In this example problem, we have a farm tractor tows a 4,400 kilogram trailer up a 21-degree incline, as I have drawn in the picture here. Just a note, I didn't draw the farm tractor just to make the picture a little bit easier. We're only concerned with the trailer, so I only drew the trailer. But it's pulling this trailer up at a steady speed of 3.0 meters per second. Now, when it says a steady speed of 3.0 meters per second, you can assume that the acceleration is 0 in this case. What force does the tractor exert on the trailer? So that's what we want to find. We want to figure out what force is being applied to the trailer from the tractor. So let's start by drawing all of my forces on what I'll call my more realistic picture, and then I'll show you why I drew two roads in just a moment. So let's start by drawing all the forces on here. Now we know that there is a force pulling this trailer up the hill. Okay, from the tractor, so we'll just call this force pull. Okay, so that's F sub P for force pull. Now, you may be tempted to draw the weight of the trailer sort of like this. Okay, you may be tempted to draw the weight like that, but that's incorrect, because what that would imply is that gravity has somehow changed, simply because we're on an incline. Now it looks like gravity is pulling sort of at an angle, but remember, you cannot change the direction of gravity, so that would be incorrect. Gravity is always straight down, period. So when you draw the weight of this trailer, it needs to be straight down, because that's the direction of gravity. So straight down, we've got the weight of the trailer acting straight down toward Earth. Now there's one more force. We know that that this trailer, okay, is being kept on this road. It's in contact with the road, so there must be a normal force pushing up from the road on the trailer, and we'll call that the normal force, okay, acting directly perpendicular to the road, and we'll call that the normal force. Okay, so because this is frictionless, we can ignore friction. Those are all the forces that we need to take into account in this scenario. Now the reason that I drew two roads is to help us draw the free body diagram. Now if you remember from the previous lessons, what we do to draw the free body diagram is we replace the object with a single point particle. So let's draw our point particle, and then we'll sketch all of our forces acting from this one single point. So we've got our force pull, pulling up the road, so that's our force pull, and we've got our normal force acting straight up, best that I can do there. Okay, so there's the normal force, and then we've got the weight acting straight down from that point. There's the weight. Okay, now there's our free body diagram. Now if you're still following the steps, we need to define a coordinate system. Now I know that all of you are really used to, I'm about to mess you up here, calling up positive y and calling right positive x. That's the traditional coordinate system, which is perfectly fine to use in this case, but you can save yourself a lot of time and a lot of hurt and a lot of pain by tilting your coordinate system. Now, what do I mean by that? What I mean by that is just imagine taking this and just rotating it slightly counterclockwise. So this is what I mean. Let's say that up the road is my positive x-axis. Down the road is my negative x-axis. Okay, and then along the line of the normal force is going to be my positive y, so up this way, that's going to be my positive y, and then acting down like this, sort of at an angle, that's going to be my negative y. Now you may say, why in the heck would I do that? It's perfectly okay to have a tilted coordinate system as long as you're consistent throughout the entire problem. Now the reason that you do it this way is that way now you can see that you've got two of your forces acting directly along the x-axis and the y-axis, which is going to make your calculations a lot easier. It may take a little bit of getting used to dealing with these rotated coordinate systems, but I can promise you that it's going to make your life a ton easier. So we are going to move away from using the traditional coordinate system to using this tilted coordinate system when we're dealing with objects on inclines. Okay? Now, this is getting a little bit messy, but I do want to make one more note on here. Now, I'm not going to go through all the geometry of proving this because I don't think that at this point that it's very beneficial. But one thing that I want you to know, and you're going to see this time and time and time again, when you tilt this coordinate system, you can automatically assume that the angle between the weight and the negative y-axis is the same angle as the angle of incline. Now, I'm not going to go through the geometry proof of this. If you're curious about it, just ask me and I'll walk through it. But for right now, let's just learn how to do this. Kind of go through the procedures here, and we're just going to remember that when we tilt the coordinate system, that angle between the negative y-axis and the weight is the same as the angle of the incline, which is 21 degrees. So this angle here, okay, that is 21 degrees. Now, since that is a little bit messy, I'm going to redraw that picture on the next slide. There we go. Now, I have it drawn here, okay, without the road, just to make it a little bit clearer, and you can see that I've got the 21 degrees between the negative y-axis and the weight. And you can see that if you just sort of imagine tilting your head, or maybe if this were drawn on a piece of paper, just tilting the piece of paper, and these two pictures are exactly the same. One is just tilted, okay? So this is actually the situation that we're dealing with for this problem. Now, just as we covered in the in-class notes, okay, forces are vectors. So now at this point, we need to break all of the vectors acting on this trailer, this point particle, into their x and y components, and then we can use the component forms of Newton's second law to solve this problem. So let's start by breaking all of these components into their x, or all of these vectors into their x and y components. Let's start with the force of the pull. Now, because we have set up our coordinate system the way that we have, you can see that the force pull is directly along the positive x-axis. Okay, so it's not going to have a y component in this situation. It's only going to have an x component. So we can say that the magnitude of the force pull, okay, is equal to the force pull in the x direction. So FPX, and we don't know what that is. Okay, and that's what we are looking for. We're looking for the force that the tractor is exerting on the trailer. So we don't know what this FPX is. The normal force is in the y direction. Actually, let's go ahead and write this out. So FPY, just to be clear, so that means FPY is 0. Okay, because it's acting directly along the positive x-axis. Now let's take a look at the normal force. Now obviously, since it's acting directly along the positive y-axis, it's not going to have an x component. So the magnitude of the normal force is going to be equal to the y component. So we have the magnitude of the normal force is equal to the normal force in the y direction. And we still don't know what that is either, so I'll just put a question mark there. And then we can go ahead and say that nx is equal to 0. So really the only one that we have to do some trig to is that weight, is the weight force. Okay, and it's going to be some simple trig. I'm going to redraw that vector just to make it a little clearer with the triangle that I'm using. So here's the weight, here's the weight, here is my negative y-axis. Okay, negative y. I'm just going to draw a line straight over to my negative y-axis, and we know that the angle is 21 degrees. Okay, so you can see that when we solve for this side of the triangle, that's going to be the x component of the weight. So we know that the bottom side of the triangle is going to be wx. And when we solve for the vertical side of the triangle, that's going to be my y components of the weight. So y, or w sub y. So doing some simple trig here. Hopefully you remember at this point that the SOHCAHTOA. So we've got, maybe let's try sine, the sine function. So sine of 21 degrees is equal to the opposite over the hypotenuse. So we'll have sine, so sine of 21 degrees, sine of 21 degrees is equal to the opposite, so wx over the magnitude of that vector, w. There we go. Okay, so rearranging, solving for Wx, we get Wx is equal to the magnitude of the weight, and that's going to be equal to, or times, sine of 21 degrees. 21 degrees. There we go. Okay, perfect. So that's going to be my x component. At this point, you may be saying, well, hang on a second. What is the magnitude? I need the magnitude to actually be able to solve for that x component, okay? Now, we haven't talked about this yet, but in a few days from now, you're going to have a lesson that explicitly talks about weight. But for right now, suffice it to say, and you may know this from your physical science class, that the weight is equal to the mass, okay, times gravity, which is also a vector because it's an acceleration. So in this case, the magnitude of the weight will be equal to the 4,400 kilograms. So 4,400 kilograms times the g, okay, which is going to be 9.81 meters per second squared. 9.81 meters per second squared. Okay, typing that into our calculator, we get approximately 43,164, and I'm not going to round this until the very end, just like we've done all year. Okay, so I'm going to keep this number. Every time I use this number, I'm going to use all the digits that are there. 43,164 newtons is the magnitude of the weight. So let's go over here, and we'll plug that in. And we know that Wx is equal to that 4,300. Let's see if we can make this fit. 43,000. 43,000. Let's leave off the comma. 43,164 newtons times sine of 21 degrees. 21 degrees. There we go. Now, typing that into our calculators, we get approximately 15,468. 15,468 newtons. Now, remember, if you're looking at your calculator right now, you probably got like 15,468.594172. Remember that I'm not rounding this number. I don't round until the very end of the problem. So I'm just using this as a placeholder. For all the future calculations, when I use this number, I'm going to use all of those digits that are in my calculator. Okay, so now our goal is to solve for the y component. So I've got just a little bit of room down here at the bottom, so it's going to get just slightly cramped, but I think you can handle it. So let's use the cosine function this time. We know that the cosine function is equal to the adjacent over the hypotenuse. So in this case, it's going to be cosine of 21 degrees. Cosine of 21 degrees is equal to the adjacent side, so Wy. So Wy over the magnitude of the hypotenuse, which is the weight, which we previously calculated as that 43,164 Newton number. So 43,164 newtons there. Okay, and just hitting this with an algebra stick, we find that Wy is equal to, let's see here, I got 297 newtons there. Okay, now I'm going to check my signs before I continue on. Okay, so we know that we are down here in the third quadrant, so we know that both my x and my y have to be negative to get down there. So both of these need to have negative signs out front, so that's going to be negative and negative. Okay, now we're ready to solve. So I've on the next slide, I've compiled all of my x components and y components all into a nice list. So let's go there and check it out. So here are all of my x components and all of my y components. Now if you think about it for just a second, Okay, we're wanting to know what the force is that the trailer is exerting on, or the tractor is exerting on the trailer. So that's going to be just in our x direction. So really everything in the y direction we can just ignore because this trailer's not accelerating in the y direction. We just want to know information about the x direction. So really all we have to do is just use Newton's second law in the x direction for this case. So the sum of all forces in the x direction is going to be equal to, okay, Fpx, which we do not know, Fpx plus 0. Okay, now you can just leave that out, but just for clarity, the 0 is from the normal force in the x direction, so plus 0, and then plus negative 15,468, so minus 15,468. Now we know that the sum of all forces in a given coordinate direction is equal to the mass of the object, so in this case the trailer, times the acceleration in that direction. Let's go and plug that in. We know what the mass of the trailer is. We were told that it's 4,400 kilograms. So we've got 4,400 kilograms. 4,400 kilograms, and then the acceleration in this case, we go back to the problem, and oh yeah, I remember, this is being pulled at a steady speed of 3.0 meters per second, so we can assume that it's not accelerating at all, which makes the problem a lot easier. So in this case, our acceleration is just going to be 0, which means everything on the right-hand side goes to 0, because 0 times 4,400 is just 0. So now we have a relatively simple problem to solve here. So we get Fpx plus 0 is just Fpx minus 15,468. Now remember, I'm not using the rounded number, I'm using that whole number from my calculator, is equal to 0. Rearranging and solving, we find that the force of the pull, okay, from the tractor in the x direction is equal to 15,468. Now, because of the way that we set up our coordinate system, we know that Fpx is also equal to the magnitude of the original vector. So we can go ahead and conclude here that this, okay, is going to be equal to the magnitude of the force pull from the tractor on the trailer. Okay, now the last real step here is just to round using our sig figs. Looking back at the original problem, we've got 2 sig figs, 2 sig figs, 2 sig figs, so we round this to the magnitude Fp is equal to about 15,000 newtons. And that's our final answer. Okay, if you have any questions, just raise your hand and ask. I hope you enjoyed this problem, and have fun with this homework set.